Now, what's next? Okay, we still go with the arrays-related method or algorithms. Okay, so now we want to search for particular item in an array. Okay, so remember, a search may not be successful. Okay, let's say that I have a 1, 2, 3, 4, 5, 6 in 6 numbers inside an array, but I want to look up 7. Okay, so you should tell me there doesn't exist that 7. So we will end up with 2 kinds of algorithms. One kind is, in terms of the answer, one type is called decision problem or decision algorithm, that to decide whether that particular target is there or not. If yes, return true. No, return false. Okay? Or you can change it into a location problem. Say I want to locate it inside an array. So if it exists, give me the index, array index of my target. Okay? Or the array index of a target of the first encounter index. Maybe you have, just like what we have seen before, we have two coins of $2. Okay, then we will have to return the first encounter index. Or if you cannot find it, okay, give me -1, because -1 is so happen that it is not an index anymore, right? You won't have an index of -1. So I will use -1 to say that there is no such return values. The code itself is very easy to understand. Okay, we call it sequential search. Sequential search means that the search is done step by step. I look at the first item. Okay, if the first item is so happen to be my target, then I will return that this is a decision problem. I will return 1. Okay, and do it one by one until I encounter the end of the array. If the end of the array is reached without calling that return 1, that means that the target is not there. It's not inside the array, so I return 0. And the location problem are still the same. I call it sequential search. And the search results is just a little bit changed. I just want to find the first encounter index of that target. Okay, so I will do the search one by one. Okay, and when I hit the target, I will say return I. If it's not, that means that after I loop through the entire array, I cannot find that element, and I return -1. Okay, so you should not have any problem, right? It's easy. Now, what is not easy is, next I will give you a faster algorithm. Faster algorithm to look for a particular array item. Okay, so before I tell you why algorithm A is faster than algorithm B, so we have to analyze an algorithm first. And how to analyze the algorithm? In here, what we are looking for is how many comparison, okay, is needed before we can determine my target is at a particular location. Okay, let's say this is our what I call a performance metrics. Okay, I want to measure this. If the number is small, that means the algorithm is good. But what is the meaning of small? Okay, or under which scenario should be taken into consideration, right? Whether we are talking about a best case, what is the best case? What is the best case? 0. The array index 0 is the target. So you just need one comparison. What is the worst case? The last one. I give you one more time. Okay, not the last one. The worst case is not the last one.
No such thing.
Yes, no such things. Yeah, because the last one you still miss one comparison, right? So under this, okay, we have the worst case, but so happen that your answer and my answer give the same number of comparison, right? Give the same number of comparison. Okay? How about average case? Average case needs some analysis. So what is the meaning of average case? Let's say I run the algorithm for 1 million times. 1 million times. Every time I count a number of comparison. So under 1 million times, basically on average, how many comparison we need? This is the average case analysis. Okay? So best case and the worst case. You already give me the answer. You give me the best case, you give me the worst case. Very good. Now, how about the average case? Average case is, that's why I asked you whether you know probability or not. Okay? So let's have a very brief introduction. The brief introduction is like this. Let's say, because we understand that no matter it is a worst case or best case, we can only focus on the case that we can find the item. Because if we cannot find the item, it always goes to the worst case. So let's assume that we can always find the items. And then what? Let's say we pick a number. Let's say we already fixed this 5 number. Okay, we randomly pick 1 to 5. So the chance, as assume that the selection is under uniform distribution. Okay, then each number will be chosen, okay, to be my target of a chance 1 over 5. Okay, let's say I under this 1 over 5 control of the probability, I pick 3. Okay, I don't know why I picked 3. Now with this 3, if I want to count how many comparisons before I know that 3 is inside. Basically, we did 3 comparisons, right? Compare 1, compare 2, and compare 3, done. I found it. Okay? So I would say C is equal to 3. Probability 1 over 5. Now, basically, this is a random variable, right? The random variable says if the random variable C gives me 3, okay, the probability of C equal to 3 is 1 over 5. The probability of C equal to 4 is also of probability 1 over 5. And what if we scale it up? I don't want 1 over 5. I want to have a general case. To scale it up, we need to compute its expected value. Okay? The expectations of how many comparisons before I found that element. Okay? So let's declare our random variable Cn. The n stands for the length of the array. Okay? And assume that every items are distinct. Okay? So that I can just cut out all the complexity in the analysis. Okay? Now let's say we want to count how many comparisons before I found the number. It basically means the equivalence. The equivalence that the target is if Cn equal to k. Cn equal to k. It just happened that it means I look for n comparison and I found a number. And so I write it down like this. Cn equal to k is actually the target element is in the k position. And remember, Cn is the number of comparison. No problem, right? Now, how about the probability? Cn equal to k. What is the probability that we have Cn equal to k? If I select the set of numbers inside the array with a uniform distribution, will always be 1 over n, right? So no matter Cn equal to k or Cn equal to k plus 1 or Cn equal to 1 or 2, they are all of the same probability. Okay? So when we compute as expected comparison, okay, that is a ECN. So do you still remember how to calculate expectation? Expectation is the summation of the probability of the events to happen times its time is the value. So when Cn equal to k, I know that the number of comparison is just k. If Cn equal to 1, the number of comparison is equal to 1. But the probability Pcn equal to k or Cn equal to 1, they are all equal. Now, up to this step, any problem? No problem. Then I can extract this and make it into 1 over n. And why I have a k here? The k is the number of comparison. That means the value of Cn. Here, when it's Cn is to k, that means they have a k comparison. Then by simple algebra, we will understand that the average case comparison is approximate half of the length. Okay? No matter what is number, Okay, in average, I need to access half of the array width in order to look up a number if I use sequential search. Okay? Any problem? Any problem? This is very important. This is very important. It's tell you one thing. As n grows, your time in spending to look up an element grows proportionally and linearly with the number of n. Right? So the bigger the array, the more time you need. And this is, of course, it's more time you need, but by what proportion? It is a linear relationship. Okay, this is the time. And your n is the size of the array. So you have a linear relationship, which is, I mean, 廣東話好過冇啦 better than none. Okay, it's quite acceptable. Okay. So under this analysis, okay, you will know that the best case is 1 and useless. Right? How often I have the best case? Okay, 1 over n. Okay, if its average case is n approximately half, and the worst case is you need to scan the entire array. Now for computer science, okay, any topic of computer science, when we talk about design of an algorithm, we always look at the worst case, because this may be the time, okay, that you need to spend, and it is the longest time, the worst case scenario. So with the worst case scenario, we said that this algorithm perform what is performance, how to measure it. We call it of order n, okay, or linear time algorithm. Linear because it's grow with the n with a relationship linear relationship. Okay, so this is the analysis of this sequential search algorithm. Any questions? Any questions? Should be no, because I just seems to be make something straightforward become a math. Okay, now this is something not straightforward. I want to have performance boost. I want a faster results. I'm not satisfied with the sequential search. I introduce you a new algorithm called binary search. What's the meaning of binary search? Is very close to what we have learned, the algorithm called bisection method. Very close. Okay? And it depends on one properties. The property is the array is sorted. Okay? Previous case, I don't care about the internal structure of the array. But now I have to require that the array is sorted. Then we can have a performance boost. Okay, so let's take a look at the procedure now. Basically, it's very similar to the bisection method. We have a high, we have a low, right? Remember. Now in binary search, we have the left, we have the right. Because it's sorted, let's say it is a sorted in ascending order. So the left means the smallest item, the right means the biggest item. Okay? And because it's array length, so the right element is array length minus 1. Okay, it's a 0, 1, 2, 3, okay, and the last one is n minus 1. Okay? Then we have a target, right? So if it's target, good, it's stop. Okay? But what is the location that we are considering is the middle. It's the middle element. Okay? I have the whole range, I focus at the middle one. If the middle one is target, stop. If not, because it's sorted, very interesting. If the target, your targets, let's say I have a 1, 2, 3, 4, 5, 6, 7, 8. Okay? My target is 2. So it is on the left-hand side of the middle one. Right? So that means the range should be cut. The range should be cut, just like the bisection method. You have to cut it down. Let's say the target is smaller. Then we will shift the right-hand side. Because originally this is such a big range, I only focus on the smaller range. So move the right. Reverse. That is, the middle one is a smaller number than the target. The target is a bigger one. Then we will shift the left. Maybe you don't understand what I mean. Let's see some animations. So if your printer looks out, sorry, I have so many pages of animation this time. Okay, so animation is like this. we have the original starting position, the head and the tail, okay? And my target is 5. Yeah, I see the index 6, okay? Yeah, I want to adjust to look for the index 6, so, but yeah, okay. Then what is the procedure? For one run, the one run is always look for the middle one. Now, what is the middle one? I just make up an array of 9 elements so that you can find the middle one to be the 4, right? It's 0 plus 8 divided by 2 equal to 4, okay? Then what is my target? My target is 5, and this is a sorted array. It's a sorted array. So the middle one give me 77, and that means that my target 5 is in this region. It's in this region. It's no longer on the region bigger than the middle, and not even the middle. The middle is not under my consideration. I exclude the middle and all slot bigger than the middle. So my consideration will be starting from 0 to my new right. My new right, how to compute it, okay? To compute it is right is equal to middle minus 1. So I don't use middle anymore because middle is useless. I already know that middle is not my target. Now, what's next? Next, this range, I never consider it anymore, okay? So in terms of searching, it means that I cut out half of the storage. The half of the storage, I don't need to care anymore. Just one comparison. I already know that I can cut out half of the slots. Now take back a look back into the sequential search. After I find one slot, and the slot is not my target, I can only exclude that slot. Okay? Now you can see how fast this algorithm will be. With one comparison, I can already cancel out, remove out the half of the storage. And what's next? Next is I still go on with this range, okay, and find the middle. Now because this time I have an even number. Now look at how the performance, how the algorithm perform. I have a 3 and then 2, 3 and then 0 add together divide by 2 is 1.5, but it's an integer. So during integer division, it's 1. Okay? So I will have the middle here. It so happened that middle is still bigger than 5. Middle is still bigger than 5. So I already know that the index number 1, 2, 3 are all not under my consideration. I can cut them out. Again, this time it's not cutting out half, cutting out 75% of the slots. I have 5. I originally have 4, not 5. 5 here. Okay. 4 here. I originally have 4 now. I know that 3 of them are useless with one more comparison. Then I will have my new right. Then left, right, middle all point to the same slots. Now the decisions is because so happened this is 5. So happened this is 5. Then I found my target. Now what if my target changed to 3? Then you will go through one more loop of changing the left or right or middle. Then you will find the algorithm stops. Okay? So I give you one more example. This example is having 3 rounds and we go to the target. Now another example is on the other extreme here, 2000. Okay? So this time we need one more iterations. Okay, so after this comparison, we know that the 77 is a smaller guy, so the target must be in this range. Okay? Then we move half of the storage, basically we don't need it, and do another comparison and computation, know that this is the middle, and still it is bigger. I mean, my target is still bigger, so these 2 slots, I can remove them. Okay, so I have only 2 slots left. It's so unlucky, very unlucky that after comparison, the left and the middle give me the same number. Okay? But the left is not the one that I want. Okay, so I will take one more step, cancel 7, and move the left to the slot 8. And then I found it. Now this time I need 4 rounds. Okay? Now you can see how fast this algorithm converge. Okay, every time it cut out half of the space, every time it cut out half of the space, okay, as in this illustration show, later I will show you the code. Cut out half of the space, half of the space, and guide you to the target, 2000. Now you can see that the number of comparison, okay, every time will be sacrificing this amount of space. Now, by analysis, okay, how fast this algorithm perform? Now we will take a look at it. The analysis is, okay, we will do a worst case analysis. Yeah, the best case and is very easy, right? Just a below and then it's got it. Okay, average case, basically I don't need average case because if I know the worst case, basically we don't need the average case. Now how about worst case analysis? What is this table? This table, I just want to show you the relationship between the halving operation. Okay, we have halving operation now. The halving operation versus the length of the array. If the array have only one element, basically you don't need to half, right? With one comparison, you already know that whether the element is the target is that element or not. Now how about we have 2 slots or 3 slots? Okay, then at least you will have a 1 halving operations. Okay, you compare once and oh, it's not a target, then you half for once. And because this is free, halving it give you 1. Okay, 3 halving it give you 1. Integer division, right? So you will end up with 1 element left. Whether that element after halving is your target or not, basically you need 1 more comparison. So if it's 2 or 3 length, you need 2 comparison. If it's a bigger array in the range of 4 to 7, you need 3 comparison because you need 2 halving in order to tell you that the target is not there. Bigger, from 8 to the length 15, you need 4 halving comparison, and then 5 halving, and so on and so forth. Okay? So how to analyze the complexity? Okay, very simple. How simple it is. Let's make an assumption first, okay, in order to have an easier discussion. The assumption is the length of an array is so happen to be a power of 2. So that means that either it is 2, 4, 8, 16, so on and so forth. Okay? Then let k be the number of iterations, or you can reduce the number of iterations to comparison plus 1. Yeah, basically after you halve it, you have to compare 1 more time. So k is just a halving operations, and k plus 1 will be the number of comparison. Okay? Now the iteration k, okay? How many times we need basically to reduce the range to the width of 1? How many do we need it? Okay, so basically it means that I keep on doing halving for n divided by 2, divided by 2, divided by 2, such that I reduce the whole range into 1. And because of that 1 is not the target, then I will declare that, boom, that target is not there. Okay, so it's very simple algebra. I will know that the number of comparison or the number of halving is of the order log 2n. Okay, so I will call it a log-based complexity. Much faster than linear time complexity. Later I will show you a graph. Okay, so how about n is not a power of 2? Yeah, basically this table can tell you. If it so happens to be a power of 2, look at the pattern. If it so happens to be a power of 2, so in this boundary from 7 to x, 7 is the power of 2, x is the power of 2, the number of comparison just increased by 1. And here, the number of comparison just increased by 1. So basically, if it is a number okay, between 2 to the power 3 and 2 to the power 4. Okay, I will say that this range containing the same amount of comparison needed. Okay. Now that means that the binary search, we just need one more operation to sort the array first, and then we can have a very, very fast comparison time. Okay. So how fast it is? We call it of an order of log 2n. Using words cannot describe how fast it is. Let's see this graph. Okay, this graph is explained. This blue, no, sorry, green. This green line, okay, is log 2n. Okay, it's log 2n. You will see that the line grows very slowly, right? Grow very slowly. But how about linear? Linear is a y to x. Okay, y to x grow like this. Okay, as the array length grows, this gap will also grow. I have a plot for, let me find it out. Should be in my Dropbox. Hey, what happened? Google want me to update things. Okay, I have having in the Dropbox that I have a plot. Okay, so this plot is to plot the difference when the array length is 100. See? If I plot it in the 1000, basically you cannot see this green line because the scale is basically is of another scale. Now, then you know that if I use binary search, basically the number of comparison or the running time is much smaller compared to the sequential search. Yeah. So in later back to the lab, we have a problem. We have a problem to search over an array. Okay, we start everything small. Okay, we don't give you a say, oh, this is a 1 billion items. Okay, search for me. Okay, we only start with 90 items. Okay, you can still choose whether to use sequential search because 90. Okay, not 90 billion. 90, you can still search over it using sequential search or binary search. Is up to you. Okay, and the code for binary search is here. Okay, the loop will stop when the left and the right interchange their position. So what is the meaning of interchanging their position? Okay, because of these two operations. These two operations will guide the right going to the left side, right? The right go to left side because the middle is on the left of right. Okay, if so happen the middle is just equal to the right, so happen they are overlap, I will further push it to the left for one more slot. Okay, why I have to emphasize this? Okay, not this figure. This figure, the left, the right, the middle is the same guy. Now, if I say that the target is somewhere here, say 4. Okay. 4, smaller than the first item, then the right will further push to this direction because of this -1 operation. Then the right will, for the first time, smaller than the left, which is not possible. Which is not possible. Okay? For another condition, let's see this illustration. This illustration is, let's say my target is 1 million. It's here. Okay, outside the array. So the algorithm goes on, the algorithm don't know about this, and try to push the left, okay, all the way back, okay. Basically, we're pushing left. We have new left, we have new left, we have new left, okay. And how about if I further push it, then it will push to this direction for the left. For the right, it won't change. So the right and the left, for the first time, they interchange the position. When I detect the interchanging of the position, that means it is a time to stop the algorithm, and tell the user, tell the caller that it doesn't exist. Okay? Any questions? Any questions? Yeah, you may need to write the code in order to understand this. Okay? Understand this? Well, basically, the analysis is something extra to you. Okay, it will help you to understand, oh, binary search is a good thing. No? I think I don't have enough time to talk about this. Yeah, but I have lab exercise. How come? Okay. Let's go on for a while. Okay. So statistical applications. So what are statistical applications? Yeah, basically it's just the mean, the standard deviation, the mean, the max, the median, right? What are the remainings? Yeah, maybe the quartiles. The quartile is just a change. Okay, you only need the median, right? If seldom work for the quartiles. So how about the mean and the sum? Now this program, I write it on purpose, and there is at least 3 potential parts. Now basically what this program is doing is try to find out the mean. Mean is easy, right? You find out the sum. Find out the sum and then divide the sum with the length. I can locate 3 parts. Can you find all? I give you 2 minutes. And on the next page, I have a lot better implementation. Oh, this is not a bug. Okay. Why? I found something wrong. Okay, come on. Wow, crash. Okay, good. Hey, how come I cannot start it? Okay, good. This is not results. Okay, this is sum. Okay. Yeah, sorry, I make a mistake. So this is a why the course doesn't appear? I forget about this. Okay, this is not results. Okay, this is sum. I write the wrong variables. Okay, so 4 bucks. One more minute. Two are very easy to find. The last spot is very hard to find. Seconds. Okay. What is the first part? Then maybe you. What is the first part? Yeah, sum didn't initialize. Good. This first part. Second one. Can you find second part? Line, which line? 7. What's the problem with 7? Yeah, integer division. Okay, remember, average or mean. Yeah, we basically need a double. Okay, so remember there's a potential bug, integer division. Last bug. The bug is not about the syntax. Can anybody try? Do you know it?
Overflow of sum.
Yes. Yes, that's the potential bug. While you are doing the sum, okay, when you add, you may have a chance that you overflow. Okay, you overflow. Now remember, every items that I give you can be able to store within the integer range, right? I give you an integer in the square shape. So its average should be smaller than or equal to its max, right? An average number should be smaller than or equal to the max item in the array. So it shouldn't have any problem while you are computing the average. It shouldn't have any overflow. But if you have overflow, you keep on adding, you will have a chance that you overflow. Okay? How to fix it? Now, to fix it is very simple. Basically, just play around a bit with math. Play around a bit with math. The math say that I need to compute the sum and then divide it using the length. Why don't we do this? At every step, after I add it, I divide it by the length. Any bugs here? Any bugs here?
I think the division should be done in line 5.
Yes. Yes. Be careful, okay? The division should not be done there. Okay, the division should be done here. Okay, one line upper. Okay. So remember this. Yeah. So my slide is bad. I don't tell you the bugs. Okay. If you do a blind copy and paste, sorry. Okay. Remember this. The division should take place first. Okay. It's not adding it and do a division. Okay. So how about standard deviation? This should be changed, of course. Okay, so I should have used the PowerPoint to change it. Okay, yeah, maybe I change it back. Okay, or I put a mine in there. Or I put a trap here that everybody copy and paste it. Okay, very easy in computing a standard deviation. Still remember what is standard deviation? Standard deviation is the distance. Yeah, the physical meaning is the distance from the mean and average all the distance. No, you seems to don't know. How many of you don't know what is standard deviation? Yeah, don't just memorize the equation. Memorize the equation doesn't make sense. Okay, you should understand its physical meaning. The meaning is y is a square because if you want to measure the distance should be a positive integer. Okay, so then you will have a average minus the array element, and we call this type of computation two-pass implementation. Means that we have to go through the array 2 times. The first time I compute the mean. Second time I will use the array elements, okay, to compute the standard deviation. 2-pass. But there exists a 1-pass implementation. But I guess you may not know about this 1-pass implementation because it play around with some random variables. Okay, I learned about this when I entered the university. Okay, so I put a link here. Okay, if you have a chance to take statistics course, okay, it will be a first few weeks lectures. Okay, to talk about how to compute variance. Okay, and when you talk about how to compute variance using a definition from a random variables, then you will know what is the meaning of this 1-pass implementation. How about median? Median is the middle value. Okay, now remember, middle value doesn't mean the middle position. Okay, so it depends on whether the length of the array is a odd number or an even number. If the length of the array is an odd number, then it will be the same for middle value and middle position. Just happen to be the same guy. If it's an odd number. If it's an even number, then it will be these two numbers these two array index, okay, these two array index, average them out, and become the middle value. Remember, median means middle value, not middle items. Now, how to get a median? Very simple. The median is you sort the array, and compute this. Okay, I don't give you codes because it's going to be a lab exercise. They're very simple. Okay. Okay, should I go on? Yes, I have to go on. Yeah, this time is something about math. Okay, recursion. I know that since I was in a high school. Okay, a high school means that during my time I have 7 years of secondary school study. The last 2, okay, we encounter many math definitions, many math theorems, proofs. Okay, then I start to know that many math definition is basically in a form using itself to do the definitions. Let's say the factorial. Factorial, basically, you don't need to say that, n factorial is equal to 1 times 2 times 3 up to n. In mathematics, we can define it in this way, right? If n is 0, okay, then n factorial is 1. If it is not 0, okay, basically it's bigger than 0, then n factorial is equal to n times n minus 1 factorial, right? Yeah, very, very trivial, right? How about power? Power we can also write in this way, okay? If it's 0, x to the power n is 0, I mean, x to the power n would be 1. Else, x to the power n is equal to x times x to the power n minus 1. Okay, this is a recursive definition. Basically, the function's factorial is defined by itself. Understand? Now, why we have to learn this? Because many math equations write in this way. Just how many weeks before? About 2 or 3 weeks. Okay, one of my very old friends. Okay, he's graduated more than 10 years, so he's come back to visit me. Okay, he is now working in an iBank firm, and they hire people write recursions using a programming language called OCaml. Yeah, OCaml is a language that's extremely good at running recursions. Okay, there's only one job of this language is to run recursions. Okay, and in many people in physics department, math departments, they are also very good at coming up with recursive algorithms. Okay, because just math is always love to do this. Okay, and many famous definitions to define this way. And with this kind of definitions, basically we can change it into code very efficiently. Okay, I just do a 1-1 corresponding transformation. Yeah, just spend a while. I did the same. I just changed the factorial description and factorial become a function called factorial n, integer n. Because the factorial is a multiplication over integers, so my return type is also integer. It should have a problem, but I just put now integer here. Okay, so you can find that if it is equal to 0, if it else, if it's equal to 0, I will return 1. If it's not equal to 0, I assume that it is a positive integer. Then what? Then I will return n times factorial n minus 1, just like the math definition. Okay, so how a C program, okay, will work if I say want to compute 3 factorial. Okay, I can only have 3. Okay, 4 then I will write it here. Now, what is the meaning? The meaning is I will trace the code like this. I first input n equal to 3. Okay, n 3. That means n is equal to 3 is not equal to 0. So I won't take the true if true part. I will take the else part. Else say that please return a value n times n minus 1 factorial. So as if it's just going to prepare a value of this here. Yeah, I cannot use a mouse. Okay, here 3 times f2. Okay, I don't have space, so I don't write factorial here. I just write f. Let's go on. How about the next layer? Because of this f2, if I don't have the f2's value, I cannot go on. So the computer knows that I need to compute f2 before I can return the value of f3. So I will compute f2. Now f2 fall into this category, same category as before, because it's fall into the else part. So it will compute 2 times f1. Again, because I don't have f1 value, so I have to compute f1 again. Then I need to compute again because f n is equal to 1 not 0. I also go to the else part, so it becomes 1 times f0. How about next? Next is computing f0. Now f0, I can immediately know that, oh, return 1. So I will return 1 here. Should be no problem, right? Just calling layer by layer, layer by layer. Okay, so this value will start a chain of return statement. Okay, this return means that I create f0 value now. It becomes 1 times 1. But how about this guy? This guy will be destroyed. Okay, because the functions already return. You return 1. So this layer of code is destroyed. Okay, it's destroyed, f0 is gone. Then I have 1 times 1 now. So in this layer, 1 times 1, so I will return 1 to the upper layer. 1 to upper layer, and it basically means that f1 is equal to 1. So it becomes 2 times 1. And then return 2, 3 times 2, and eventually give me 3 factorial equal to 6. Long path, right? But while I execute this program, it's extremely fast. Okay, don't think that, wow, that long path all the way down, call, and then return. Okay, but it's a computer, right? Working as a million of hertz in a second. Okay, so believe in him, he can do it. He can do it. Okay, so how about power? Okay, because we don't have time, I just skip it. Okay, because I didn't prepare the slide for power, because power is just very close to factorial. Any questions about factorial using recursion? Okay? If you write recursion, now remember one thing. The recursion famous part about it is not about the recursive definition, okay? The recursive definition is, every textbook will write it, but how about you stop it? What we call the termination condition. If you miss the termination condition, yeah, I mean the math books won't tell about you. Math book has a termination condition. No, it never mentioned this. Usually in programming books, okay, we will mention that in writing recursion, we need something called termination condition. What is termination condition? Is the line 2 and 3. Line 2 and 3 determine the time that I should stop the recursion. You can see previous slides, right? I'm not digging deep to, here, okay? I will just stop at f0 because f0 is to terminate the recursion sequence, okay? It starts the chain of return. So I will call this the termination condition. If you miss out the termination condition, you will have a disaster. And the disaster name is called Stack Overflow. And this is not a website name, okay? Yeah, so happen the website name use the name Stack Overflow. Okay? The error, we call it Stack Overflow. You may not know what is stack, okay? Because stack is supposed to be taught in another course called data structure. Okay? If you want to know what is a Stack Overflow, click on this link. Okay? There is a very old professor, very boring. Okay, usually old professor is very boring. Talk about what is a stack and a recursion. Okay? You can take a look at the stack implementation. Okay, so we still have Fibonacci number. Watch the video and then we go back because at that place I cannot play video in a good manner. Okay, so what is Fibonacci number? I don't need to talk about it. We have a very beautiful tech talk to talk about it. Yeah, tech talk here. I know you need transcript. Okay. Yeah. No. You need subtitle, right? Which one? Which one? English lah. Learn something. Okay. What loading? Okay. I think it's already loaded. Okay. Now I push it to the full screen.
So why do we learn mathematics? Essentially for three reasons: calculation, application, and last, and unfortunately least in terms of the time we give it, inspiration. Mathematics is the science of patterns, and we study it to learn how to think logically, critically, and creatively. But too much of the mathematics that we learn in school is not effectively motivated. And when our students ask, why are we learning this? And they often hear that they'll need it in an upcoming math class or on a future test. But wouldn't it be great if every once in a while we did mathematics simply because it was fun or beautiful or because it excited the mind? Now I know many people have not had the opportunity.
Do you know what is this? Never seen this. Never seen this. This is called fractal drawing. Yeah. I mean, where can you find a course? I take a GE course to understand this. Yeah, a GE course talk about mathematics. Oh, very horrible. Yeah, it's called fractal.
To see how this can happen. So let me give you a quick example with my favorite collection of numbers, the Fibonacci numbers. Yeah, I already have Fibonacci fans here. That's great. Now these numbers can be appreciated in many different ways. From the standpoint of calculation, they're as easy to understand as 1 plus 1, which is 2. Then 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. Indeed, the person we call Fibonacci was actually named Leonardo of Pisa, and these numbers appear in his book, Liber Abaci, which taught the Western world the methods of arithmetic that we use today. In terms of applications, Fibonacci numbers appear in nature surprisingly often. The number of petals on a flower is typically a Fibonacci number, or the number of spirals on a sunflower or a pineapple tends to be a Fibonacci number as well. In fact, there are many more applications of Fibonacci numbers, but what I find most inspirational about them are the beautiful number patterns they display. Let me show you one of my favorites. Suppose you like to square numbers. And frankly, who doesn't? Let's look at the squares of the first few Fibonacci numbers. Okay, so 1 squared is 1, 2 squared is 4, 3 squared is 9, 5 squared is 25, and so on. All right, now, it's no surprise that when you add consecutive Fibonacci numbers, you get the next Fibonacci number, right? That's how they're created. But you wouldn't expect anything special to happen when you add the squares together. But check this out. 1 plus 1 gives us 2, and 1 plus 4 gives us 5. And 4 plus 9 is 13, 9 plus 25 is 34, and yes, the pattern continues. In fact, here's another one. Suppose you wanted to look at adding up the squares of the first few Fibonacci numbers. Let's see what we get there. So 1 plus 1 plus 4 is 6. Add 9 to that, we get 15. Add 25, we get 40. Add 64, we get 104. Now look at those numbers. Those are not Fibonacci numbers, but if you look at them closely, you'll see the Fibonacci numbers buried inside of them. You see it? I'll show it to you. 6 is 2 times 3, 15 is 3 times 5, 40 is 5 times 8, 2, 3, 5, 8. Who do we appreciate? Fibonacci, of course. Now, as much fun as it is to discover these patterns, it's even more satisfying to understand why they are true. Let's look at that last equation. Why should the squares of 1, 1, 2, 3, 5, and 8 add up to 8 times 13? I'll show you by drawing a simple picture. All right, we'll start with a 1 by 1 square, And next to that, put another 1 by 1 square. Together they form a 1 by 2 rectangle. Beneath that, I'll put a 2 by 2 square. And next to that, a 3 by 3 square. Beneath that, a 5 by 5 square, and then an 8 by 8 square, creating one giant rectangle, right? Now let me ask you a simple question. What is the area of the rectangle? Well, on the one hand, it's the sum of the areas of the squares inside it, right? Just as we created it. It's 1 squared plus 1 squared plus 2 squared plus 3 squared plus 5 squared plus 8 squared, right? That's the area. On the other hand, because it's a rectangle, the area is equal to its height times its base. And the height is clearly 8, and the base is 5 plus 8, which is the next Fibonacci number, 13. Right? So the area is also 8 times 13. Since we've correctly calculated the area 2 different ways, they have to be the same number. And that's why the squares of 1, 1, 2, 3, 5, and 8 add up to 8 times 13. Now, if we continue this process, we'll generate rectangles of the form 13 by 21, 21 by 34, and so on. Now check this out. If you divide 13 by 8, you get 1.625. And if you divide the larger number by the smaller number, then these ratios get closer and closer to about 1.618, known to many people as the golden ratio, a number which has fascinated mathematicians, scientists, and artists for centuries. Now, I show all this to you because, like so much of mathematics, there's a beautiful side to it that I fear does not get enough attention in our schools. We spend lots of time learning about calculation, but let's not forget about application, including perhaps the most important application of all, learning how to think. If I could summarize this in one sentence, it would be this. Mathematics is not just solving for X, it's also figuring out Y. Thank you very much.
Okay, so today we will go to the drawing part, the calculations. Okay, back to the lab. We will have our exercise waiting for you. Generation of Fibonacci numbers. Okay, yeah, to generate, I can't remember the first few numbers. The basics is the first 20 Fibonacci numbers. You will be surprised that Fibonacci number, the 21, okay, is already very big. Okay, so after you finish the first 2 questions, okay, I will talk about how to generate a huge Fibonacci number, okay, F90. So what is the problem? Okay, when you have finished the 2 questions, I will tell you what is the problem. It's about computation speed. Okay, extremely slow if you want to compute F90. Okay, so the Fibonacci number recursive formula is like this. Okay, we will go to the lab and let's do the first 2 exercises.